All right, so today's notes are on distances between points and lines in space. And just like the other notes that we've been doing, the important thing here is to know what you need and what you have and find out the pieces. So first thing, the distance between a point and a plane. Now, one of the important things here is that there is an implied word in there, and it's the shortest distance, because if I have a plane and I have this point, when I'm talking about the distance, I don't want the distance like this. That would be silly. I want the perpendicular distance, which would be this thing right here. So if I want the shortest distance between a plane and a point, really what ends up happening is it's really a projection. If you remember projections, those are all by like the shadow that a vector makes on another vector. So technically it'd be like the shadow that this point makes on here. And if I could find that distance, I'd be good to go. Well, instead of doing that, there's kind of a more straightforward way, an easier way to remember it. And the formula for distance is PQ dot n, take the absolute value, and put that over the magnitude of n, where n is the normal vector to the plane, and PQ is a vector connecting a point not in the plane to a point on the plane, any point you can find at all. All right, so PQ dot n over n is really finding the projection of this vector onto this vector right here. But again, you don't really need to remember the projection formula if you remember this. And I will give that formula to you, so there's no need to memorize it. If you take Calc 3 in college, your professors are going to want you to, but I don't really care because I want you to know how to do calculus, not just memorize calculus. So that being said, find the distance between the point 3, negative 1, 5, and this plane. So if I need the distance between a point and a plane, what I really need to find is first the vector PQ, where one of those is on the plane and one of those is not. So this is Q, the point on the plane. I'm sorry, Q is the point I'm looking for. P is the point on the plane. And the easiest point on the plane that I can find is 7, 0, 0. Or maybe 0, 7, 0. Or maybe 5, negative 1, 0. There's a lot of different things, but basically any point that would solve this equation and make it true will work. So here's P, here's Q. I need to do PQ dot n over n. So PQ is going to be the vector 7 to 3 is negative 4, 0 to negative 1, 0 to 5. And n is the normal vector to the plane, which is 1, 1, negative 2. That's just the coefficients from here. So my distance is going to be PQ dot n. Remember, when you dot things, you multiply the components together and then add. So it's going to be the absolute value of negative 4 minus 1 minus 10. Those are absolute values, not ones. Divided by the magnitude of n, which is 1 squared plus 1 squared plus 2 squared. So my distance here is going to be 15 over the square root of 6. And I don't care if it's in simplest radical form, that works for me. So 15 over radical 6, that's the distance between the point and the plane. If I want to come down here and find the distance between parallel planes, first think about what that means. I got a plane up here, I got a plane down there. If I want this distance, I basically need to find 2 points and find the distance between them, which really means I don't need this other plane at all. I can just kind of get rid of this other plane and say, wait a minute, the distance between 2 parallel planes is like the distance between a point and a plane. So my P and my Q just become points on one and then the other plane. So point P can again be 7, 0, 0. Point Q can be 17, 0, 0. So then vector PQ is the vector 10, 0, 0. And n would be the same vector for both of these, which is going to be 1, 1, negative 2. So the distance between them is going to be the dot product, which is 10, over the magnitude of n, which is 6. Voila, distance between the planes. And then last but not least on this side, first show that the line of intersection of these planes is parallel to that plane. All right, so let's do that first. The line of intersection of 2 planes. Well, if I want the line of intersection, I need to cross the normal vectors of the planes to get the direction vector for the line. So I need to cross P1 and P2. So I'm crossing I, J, K, 1, 1, negative 2, 1, 3, negative 2. And when I cross those, I get negative 2 plus 6 is 4, minus J, negative 2 plus 2 is 0, plus K, 3 minus 1 is 2. So my vector is 4, 0, 2. This is the direction vector for the line. Now, if I want to show that the line of intersection is parallel to this plane, I don't actually need the entire line. Things will be parallel based on their vectors alone. So now let's think about this. If this is a plane and this is a line that I want to show is parallel to that plane, I'm actually not going to show parallelism. I'm going to show perpendicularity because the plane is defined by its normal vector and the line is defined by its direction vector. So I want to show that L dotted with N equals 0, because if a dot product equals 0, then L and N are perpendicular, which means the line is parallel to the plane. Let me say that again. If L and N are perpendicular, that means L is parallel to the plane because the plane is defined by its perpendicular vector. So I want to show that L dotted with N equals 0. So I want to show that 2, 5, negative 4, this plane, dotted with 4, 0, 2, that's going to equal 8 plus 0 minus 8, which does equal 0. So therefore, the line is perpendicular, well, the line's vector is perpendicular to vector n, which means the line is parallel to the plane. Then find the distance from the line to the plane. Well, if I want to find the distance from this line to this plane, I can pick any point I want on the line and then find that distance. So the point on the line is going to be Q. All right, now that's going to be the tough part. I need a point on the line. So how do I find the point on a line of intersection? I make it up. So to find Q, I'm going to let x equal 0 to find the point on this line that I've started. So if I let x equal 0, I have y minus 2z equals 7 and 3y minus 2z equals 7. I'm going to subtract these. I'm going to get negative 2y equals 0, so y equals 0. And if x equals 0 and y equals 0, if y equals 0, then z is 7 over negative 2, which is negative 7 halves or negative 3.5. So then Q, I'm running out of room here, so then Q is now the point 0, 0, negative 3.5. That's the point I'm finding. Now I need a point on the plane, which is a point on this plane. I need to get 7, so I'm going to do 1, 1, 0, so that I get 7. So then vector PQ is negative 1, negative 1, negative 3.5. N is, where was N? Here we go. N is 2, 5, negative 4. So my distance is their dot product, which is going to be the absolute value of negative 2 minus 5 plus 14 over the square root of 2 squared plus 5 squared plus 4 squared. I am running out of room. I'm sorry, this is so tiny. So let's see. 14 minus 7 is 7. And I have 25 plus 16 is 41 plus 4, I think, is the square root of 45. Whew! That's a lot of work. Okay? Hopefully that made sense. I'm sorry it was such a mess. I started running out of room here. But long story short, if I want to find the distance between a line and a plane, I need a point on the line, and I need to find the point on the plane. In order to get the point on the line, I had to find the cross product to get the line's direction vector, and then I had to do that little system of equations over here to find the point on the line. All right, that one took a while. Distance between a point and a line in space instead of a point and a plane, you need to use a cross product, because if I want to find the distance between a point and a line, I need to make sure that I have this perpendicular distance right here, and the only way to get a perpendicular distance is going to be to do a cross product. We didn't need to do it for planes because planes are defined by their perpendicular vectors. Since lines are defined by their direction vector, I need some kind of perpendicular, which is why the cross product becomes involved. So the distance between a point and a line is the cross product of PQ dot U over the magnitude of U, the magnitude of the cross product over the magnitude of U, where PQ again is a point not on the line and a point on the line. Technically you could do QP also, doesn't really matter. All right, so if I want to use that distance formula, I need 2 points, I need a direction vector for the line. Fantastic. So this would be Q. P is a point on the line, which is -7, -1, 0. It's embedded right in the line thing there. So PQ, the vector, is going to be 9, 4, 4. U, which is the direction vector for the line, 2, 3, 9. It's just the coefficients of T. So if I do PQ cross U, I can actually do it right here. If you want, think of this as kind of a setup for cross product right now because they're stacked. So PQ cross U is going to be 36 minus 12. See it? 36 minus 12 is 24. 81 minus 8 negated is going to be -73. And 27 minus 8 is going to be 19. Ooh, that's a big one. So my distance is the magnitude of PQ, 24 squared, 73 squared, 19 squared. And the magnitude of U, 2 squared plus 3 squared plus 9 squared, which is going to be some gigantic number down here. Let's see, I've got 81 and 9 is 94 on that. And then for PQ, I'm going to do it off screen here. If I really thought about it long enough, I could do that in my head, but I really don't feel like it because I'm recording this early in the morning and I don't trust my math right now. 6266 up here. I don't know why that 2 is so tiny. 6266. So there's your distance between your point and your line. What if I want distance between parallel lines? Well, it's a lot like distance between parallel planes. I still need points on each. And then basically I find this distance right here. So I need, again, PQ cross U over the magnitude of U. So I need, let's see, a point up here and a point down there to be P and Q respectively. So P is going to be -710. Q is going to be -538. So PQ is going to be 2, 2, 8. U, the direction vector, can come from either line because they're parallel, so they both have the same direction vector. 1, -4, -4. So then PQ cross U is going to be -8 plus 32 is 24. -8 minus 8 is going to be -16, but I have to negate it. And another -8, lots of -8s. -8 minus 2 is -10. So then my distance is the square root of 24 squared plus 16 squared plus 10 squared over the magnitude of U, 1 squared plus 4 squared plus 4 squared. So on the bottom I've got 16 and 16 is 32, plus 1 is 33. And up top here, I'm doing this off screen, 24 squared plus 16 squared plus 100, 932. And there's my distance. Now here's the next question. Why can't we use this equation to find the distance between skew lines? Remember, skew lines are lines that don't touch, but aren't parallel. They're lines in different planes. So if I wanted to find the distance between skew lines, what you can kind of imagine is I need to find the point where one makes a shadow on the other. I can't just use any point. I couldn't use like this point and this point because then that would be a longer distance. So the reason I can't use it between two skew lines is this is going to have one direction vector, but that's going to have another direction vector. How do I pick which one to use? And what it really boils down to is if I want to find the distance between skew lines, I need to actually find the planes that contain those two skew lines because they would be parallel planes, and then use the distance formula to find the distance between the two parallel planes instead. So just to have it in your notes, why can or can't we use this equation? We can't because the skew lines have different direction vectors. Okay, that's terrible handwriting, but basically the skew lines have different direction vectors, so you can't use the equation for two skew lines. Instead, use distance between parallel planes, which in that case you need to find the parallel planes, and that's another equation and another note for another day. So, long story short, we've been talking a while about this. We are done now. We got to end with a joke. We're going to end with a pirate joke that I just learned last night. It's a good one. What did the pirate say on his 80th birthday? Aye, matey. All right, have a wonderful day, morning, afternoon, whatever, and we'll talk again soon.